Okay, so the other day, not yesterday, because we did the test yesterday, okay, we were talking about Newton's first law, we were talking about inertia. We ended up just kind of watching a lot of videos about why you could drift away in space, okay, if you weren't careful. So what we want to look at today is just kind of some of the nuts and bolts of forces, okay, how they work, how we represent them, okay, things like that. Okay, so our key points there we talked about the other day, what's meant by inertia. Inertia is the tendency of an object to continue doing what it is already doing in the absence of unbalanced forces. Okay, so an object will remain at rest or in motion at a constant velocity if there are no unbalanced forces. Okay, just like poor Woody, okay, when he couldn't grab onto the satellite and he floated away. Okay. Inertia is related to your mass. We talked about that. We looked at some car crash videos and we're like, oh my gosh, like if you have something small, that's really not good for you, okay? Because how much of you there is affects your tendency to keep doing what you were already doing. Okay, I use the example of a skinny sumo wrestler. Okay, they're not going to do well because they don't have the same tendency to keep doing what they're doing as a really big guy might. Okay, and so that's why usually sumo wrestlers are really, really large gentlemen. Okay. All right, and then number 4, understand that changes in inertia require a force. That's what we didn't get to, okay? Or we did talk about it a little bit, okay? We said if Woody had had any more fuel, he might have been able to do something because the fuel would have given him the ability to exert a force. If he could exert a force, then he could change his velocity. Unbalanced forces result in accelerations. Okay? If you're just standing still in the atrium, you know, and minding your own business, you just stay there. Okay? But somebody comes by you and bumps into you, you move. Okay? That's an unbalanced force. You have to counteract that or you fall down. Okay? Unbalanced forces, or net forces as we're going to call them often, okay, are going to be the things that cause acceleration. Perfect timing, Jordan. Absolutely. Okay. All right, so let's have a look at this. Now, defining the term force, okay? Very simply, a force is a push or a pull, okay? It is one or the other, right? It is anything that is acting on another object, okay? And it is going to push or pull them with a certain magnitude and direction. Force is a vector quantity, okay? Now, if we're looking at the examples here in this picture, okay, if that tow truck is pulling that car or towing that car at a constant velocity, are all the forces acting on the car balanced? What do you think? If it's going at a constant velocity, the forces are balanced. Okay? That's the only way you go at a constant velocity. If they're not balanced, you're going to accelerate in the direction of the imbalance. Okay? So, if this is being towed at a constant velocity, okay, there's a number of forces acting on the car. It's not just the force in the cable. What forces is the cable working against? What else might be acting on that car? Gravity. Yeah, gravity would be one of them. Okay? Gravity acts straight down, right? Like this. All right? Is that cable pulling somewhat upwards? Right? It's pulling at an angle, right? But it has a vertical component to it if it's angled, right? So the vertical component of that force is balancing off the force of gravity. That's why the car doesn't fall. If that car is going to move forwards, what's the horizontal component of that cable or that hook acting against? What would be resisting the movement of that car? Kyle?
Friction.
Friction. Okay, so this is a forward directed force from the cable or the truck, but there would be a backwards directed force of friction. Okay? But if it's moving at a constant velocity, they all cancel each other out. And there's no unbalanced or net force involved. Okay? This is the part of this unit that people find the trickiest. It's not the math. It's being able to pick out the forces and how they might be related to each other. Okay? There's a lot of visualization that has to go on in Unit 2. Okay? And it's tricky because you don't see the forces. In Unit 1, you could see what the object did. It was easy. Oh, well, it's displacing this forward because I watched it go that way. Okay? But the forces aren't always as easy to identify. Okay? Is gravity almost always present? Yes, but you can't see it. Okay? If we're looking at that cart right now, there's no unbalanced forces acting on that cart, but there are two forces acting on that cart, and you can't see either one of them. Okay? There's nothing like holding that, there's no string attached to that cart or anything. It's the floor and it's gravity. So we have to look a little deeper into things, and that's the tricky part. Okay? Is being able to look at a situation or a system and identify what forces are there. Okay? Here's a motion we talked about a lot in Unit 1. Projectile motion. The whole reason it happens is because the unbalanced force is, which way does that object accelerate the whole time it's flying? What force is acting that way? Gravity. Okay? That gravity, okay, that's an unbalanced force, right? And so it's going to cause that ball to accelerate at 9.81 meters per second squared the entire time it's in flight. Okay? It is the unbalanced force. Okay? If this bulldozer can push that wall over, okay, is the bulldozer the unbalanced force? It is. If the wall goes over, then it's because there was more force from the bulldozer than there was resisting the movement of it. Okay? Everybody okay with those ideas? Okay, so things to get out of this slide. Force is a vector quantity. Okay? It has magnitude and direction. It is a push or a pull. Okay. Here's another thing we do horribly, horribly wrong in North American society. If I ask you how much you weigh, don't tell me it's a personal thing, okay? But if I ask you how much you weigh, you don't ever tell me the right answer, okay? In fact, even my scale doesn't tell me the right answer, okay? It tells me my mass. It does not tell me my weight. It uses my weight to tell me what my mass is, okay? But it doesn't ever tell me my weight. If it told me my weight, it would give me a number in newtons, because that's the units for force. My weight is the force of gravity pulling on my mass. Okay? In that way, it is directly related to my mass. If my mass increases, so does my weight. Okay? But when we say the things we say in our society, like, oh man, I gotta go lift some weights. No, you're going to go lift some masses. Okay? Weight is a force. You're not going to lift forces. You can't lift forces. You can work against them, okay? But you're going to lift masses. Okay? Oh, I gotta drop some weight. No, you gotta drop some mass. You want to weigh less? Go to the moon. You'll weigh 1/6 of what you weigh here, but there won't be any less of you there. Okay? You'll still have the same mass. You'll still look the same. Okay? But you'll have less weight. Okay? Your weight is affected by gravity. Okay? And of course your mass. If you lose mass, you lose weight. Okay? Everyone follow me there? Okay? But we use those two terms interchangeably. Okay? I actually like to mess with people. Okay? If they ask me what I weigh, I actually tell them. Okay? I tell them I weigh like 785 newtons. Don't do the math, please. Okay? And then they kind of chuckle awkwardly and go somewhere else, which is awesome because I'm naturally actually an introvert. Okay? And that works for me. Okay? But I also have been truthful. Okay? I told them exactly what I weigh. They just didn't know that that's not what they wanted. Okay? You shouldn't ask somebody that, by the way. It's not a polite question. That's personal. Okay? So, yeah, weight and mass are different. Mass is how much matter is possessed by an object. Okay? How many atoms or molecules it's made up of. That's your mass. Okay? That is measured in kilograms. Weight is a force. It's the force of gravity pulling on a mass. That is measured in newtons, the units, sorry, for force. Okay, everyone understand the difference there? Okay, so what happens with your scale, okay, like I don't know what your scale says when you stand on it, okay, but like I stand on mine, and you know what it says? Get off! Because it's, it doesn't probably say that. Okay? But it reads, okay, it tells me my mass. But what it's doing is it's using a spring. So when I stand on it, my weight, the force of gravity pulling on my mass, compresses that spring. Okay? And then the spring just turns that dial, or reads it on the digital screen, whatever, okay, to tell me what my mass is based on my weight. If I took that scale somewhere else, I could get a different number. Okay? If I stood on it in our school elevator, okay, and I was moving upwards, it would tell me I weigh more. If I'm going downwards, it would tell me I weigh less. Okay? If I took it to the North Pole, it would tell me I weigh more. If I took it to the equator, it would tell me I weigh less. I don't. My mass is the same. Well, actually, I do weigh less, but my mass is exactly the same. Okay? It's lying to me somewhere. Somewhere on earth it's telling the truth. Okay? But everywhere else it's lying. I just assume it's lying because I don't like the number it shows me. But okay. Everyone with me on that? Okay? So our weight is a force. It's the force of gravity. Weight and mass are two different things. Okay? So this supertanker, tons of mass. There's a lot of matter there. Okay? Also tons of weight because it's on Earth, but tons of mass because of how much matter it possesses. This penny, very little mass. There's not nearly as much matter there. Okay, mass. Mass is a scalar quantity. It's how much of you there is. That doesn't have a direction. Your weight does. Okay? My weight's 785 newtons, down. Because that's the direction that gravity pulls me. Okay? So weight is a force. Force is a vector quantity. Mass, how much of you there is, that's a scalar quantity. Okay, so weight and mass, two entirely different things. Okay, the weight we feel when we pick up a heavy object is the force of gravity acting on the object's mass. Okay, so weight is the force of your mass. Now, formulas we're going to learn and use a lot here. Okay, force equals mass times acceleration. Okay, that is Newton's second law. We're going to spend like 2.5 weeks on that. Okay, it is probably the second most important concept in physics behind work energy theory. Okay. And this formula. They're both on your formula sheet. Okay. So this one actually says net force, so F net, N-E-T, equals mass times acceleration. This one is force of gravity, Fg. Okay? Force of gravity is mass times g. What's g? Yeah, which is what value? The acceleration due to gravity, right? Okay. Force is mass times acceleration. The force of gravity is mass times the acceleration produced by gravity. Okay? All forces are calculated that way. Okay? You can calculate any force if you know what mass it's acting on and the acceleration it produced. Okay? That's Newton's second law. Okay? What makes this one a little bit more complex is this one involves all the forces that might be acting on an object. Okay? This one only calculates gravity. Okay? So we often say for this one, F net is mass times acceleration net. Okay? Which we can get if we go net force is the vector sum of all forces. You've actually already done one of these. It was question 2 on your vector assignment. with the box in the 2 rows. Okay? That was calculating the vector sum of 2 forces. Okay? In that question, you had, I believe it was 475 newtons pushing to the west, okay, and 315 pushing to the south. Okay? And we said, okay, if I push on a box west and south, which way is it going to go? Well, it's going to go this way, right? Well, that's exactly what I would get if I did the vector sum of all the forces acting on that box. This would be my F net. That's why we do unit 1 first. You got to be able to do the vector addition stuff in order to calculate net force in this here. Okay, so we're still going to be doing a little bit of tail to head stuff. Sorry. Okay, we're still going to be a little bit of that. Okay, everybody all right with that idea? Okay, so understand Newton's first law. Okay, we can like imagine in hockey here. If a player doesn't hit a stationary puck, the puck just remains at rest on the ice. Okay, after the puck is struck, okay, it coasts on its own across the ice, slowing down only because of friction. Okay, if that ice was perfectly frictionless, would the velocity of the puck ever change? Never. It would just keep going at whatever velocity it left the stick at. Now, what's it doing while it's in contact with the stick? It's accelerating, because what's the stick doing? It's pushing on it. Okay? Acceleration occurs as long as the force acts. Once the puck leaves the stick, if it's frictionless ice, that's the velocity it will have forever. Okay? Or until another force acts on it. Okay? If it was perfectly frictionless ice. Right? But we get this idea that it's always accelerating. It's only accelerating as long as there's a force acting on it. Okay, so while it's in contact with the stick, it's going to accelerate. Okay, that and work energy theorem are the main drivers of most sports science. Okay, how many people in here watch hockey? Thank you. So modern hockey sticks are very different than the hockey sticks that I used as a kid. Okay, the hockey sticks I used as a kid were a chunk of tree. Okay, they were made out of wood, and that was it. Okay, they were a little bit flexible, but they were also big and heavy. Okay, modern sticks are made of composite materials, graphite, things that flex a lot. Okay, and so what can happen is you can exert that force for longer, both time and distance, because the stick will flex. Okay, a stick that doesn't flex doesn't give you as much time to make contact or be in contact with the puck. Okay, but a composite stick can open up, bend, okay, and increase that distance. Okay, sort of making sense? The longer you can exert that force, the longer that object will accelerate. Okay, the force you can exert is determined by you. How strong are you? Okay, but if you can do it for longer, the puck will go faster, or anything will go faster. Okay, everyone all right with that idea? So the acceleration only occurs while the forces are not balanced. Once the forces are balanced again, constant velocity. Okay, so do you think it would be possible if I had like a stack of like poker chips, okay, would it be possible to flick one at the bottom of the stack and knock out just one without knocking the stack over? Yep, should be possible. Okay, now there's some things that would affect that. Okay, the height of the stack, okay, if it gets swaying at all, then it'll have more inertia because there'll be more mass. Okay, but if I can keep it fairly steady, the heavier that stack is, the better my chances of knocking the bottom one out, because it would have more inertia because of its greater mass. Okay, there's a whole bunch of places where this is true. Anyone ever see someone do the tablecloth trick? Right, where you pull the tablecloth out from under the dishes? Okay, most people do that wrong. Okay, what's the key to doing that correctly and not breaking dishes, besides using plastic dishes? Okay, here's what most people do. They got their dishes here, they grab that tablecloth and they do this. Okay? If you lift up on the tablecloth, you lift the whole tablecloth and everything just goes. Okay? You want someone who knows how to do that trick? They roll the tablecloth up in their hands, in their fists, and they put their fists against the table. And they pull which way? Then that tablecloth slides horizontally out from underneath the dishes. Okay? You direct the force in a different direction. If those dishes are heavy, they're going to stay put. If they're light plastic dishes or paper plates, they're gone. They're going to go with it because they don't have enough inertia. The more inertia those dishes have, that is, the more mass they have, the more likely you are to pull that trick off. Okay? But the key is to pull the tablecloth down. If you're going to try that at home, go to the dollar store and get a bunch of plastic dishes. Okay? Don't put mom's best china on the table for that. Okay? Just that's never happened ever. Okay, everyone all right with that idea? Okay? Same is true like, here's a simple one. Toilet paper roll. So next time you're bored, okay? You can, if you got like a roll of toilet paper that's pretty full, grab like one square and just give it a yank. You'll probably be able to tear it off without unrolling the rest of the roll. But if that roll is half or less than half left, and you try that, you're gonna have a whole bunch of toilet paper on the floor because that roll of toilet paper doesn't have enough mass or inertia to resist that little bit of force. That's why there's perforations on the toilet paper, so you can do exactly that. If you go quick enough, okay, you'll tear the perforations and not overcome the inertia of the rest of the roll. There. Next time you're in the bathroom, you got something to do. Okay? You got a physics experiment you can try. Okay? Boring, but whatever, it works. Okay, so big thing here, guys, the definition of net force. Okay? The definition of net force is the vector sum of all the forces acting on an object. If that number is 0, you've got a Newton's first law situation. Okay? Object stays put or travels at a constant velocity. Okay, so if we're looking at this middle situation here, so we got a book on a table, okay, and there's 2 forces acting on it. There's actually 4 forces acting on it, but we'll just say there's 2, okay? There's a force to the left of 20 newtons and a force to the right of 18 newtons. So is there a net force? All right, those forces are not balanced, are they? Okay, so if those forces are not balanced, what is that book going to do? Okay, it's going to move to the left. What's that movement going to look like? Constant velocity or accelerated? Accelerated. Okay, we get constant velocity if there's no net force. As soon as there is a net or unbalanced force, then the velocity of the object has to change. Okay, so that object would accelerate to the left with 2 newtons. Okay, so that would be, I've got my cart here, okay, there's some friction that would be resisting me if I don't push very hard, okay, I'm not pushing very hard, the cart's not moving, so there's no net force. Friction is great enough that it's not allowing me to move the cart. Give it a little more of a push, then it accelerates that way. I overcome that resisting force of friction and the cart accelerates. Okay, and then as soon as I was done pushing it, did it stop almost right away? Okay, because once I was done pushing it, the only force acting on it was friction, brought it to a stop right away. Okay, everyone all right with that idea? So that's going to be the tricky part, as I said before. Looking at a situation like that and going, what are the forces involved? What do they look like? Are they big? Are they small? Which direction are they going? Okay, because right now, if I'm pushing on this cart, there's 4 forces acting on that cart. Me, friction, gravity, floor. Okay, gravity and floor cancel each other out. The object's not moving vertically. Okay, but it is moving horizontally. Okay, if it's accelerating horizontally, one of those forces is bigger than the other. Okay, this is why we spend so much time on this. There's so many different situations that we have to learn to visualize and identify. Okay, now inertia and mass. So we know those 2 things go together. Okay, the more mass you have, the greater your tendency to keep doing what you're already doing. Okay, obviously, The smaller objects here, okay, if I apply a force to those, I can make them accelerate. Okay? A car, that's not going to get a whole lot of acceleration there, but it might get a little bit because it's pretty heavy. Okay? My hopes of moving a jetliner or a supertanker, okay, with only my own brute strength are probably not likely. Okay? They have more inertia, so I'm not going to have much effect on them. Okay? Now, what if I was out in space with that supertanker? Could I accelerate the supertanker? Yep, absolutely could. Okay? I would push on the supertanker, and I would go that way, okay? And the supertanker would move ever so slightly the way I pushed it. Okay? The only reason it doesn't happen on Earth is because of friction. Friction, gravity helps produce friction, so we don't get big objects to move very easily. Okay? But if I had that airplane sitting on a sheet of perfectly frictionless ice and I could push it, I could make it move. Okay? Everybody all right with that? Would I have to still push pretty hard? Would the acceleration it produced be very big? Okay? Remember, force is mass times acceleration. I can only exert so much force. It's going to be on a gigantic mass. The acceleration I would produce would be correspondingly quite small. Okay? Okay, so quantitatively, inertia is your mass. Okay? We measure inertia in kilograms. However much of you there is, that's the measure of your inertia. Okay? And then this is Newton's first law kind of written out in words. Okay, so who's more likely to be injured in a crash? Two people are in a car. They're in the same car. Okay, car crashes into a wall. One person has a mass of 100 kilograms. The other person has a mass of 50 kilograms. Who's more likely to be injured? Lighter person, heavier person? Lighter person. Okay, lighter person's more likely to be injured, okay, simply because of this. Okay, they're both going to experience the same amount of force from the crash. Okay, but if you have a smaller mass, okay, you're dividing by a smaller number, your acceleration will be greater. Okay, that's why we put little babies in special seats in the car. Okay, they have to be more tightly secured in because of their smaller mass. We don't want them to move around a lot. Okay, so we secure light. That's why a person. What do you have to weigh now? It's see, I just did it. What does your mass have to be to get into to be in the front seat safely? 80 pounds. Okay, you got to have a mass of 80 pounds if you want to safely sit in the front seat. Okay, back seat's better if you're smaller. Okay, rear-facing car seat, same thing. We want to cushion those small masses, okay, because they can be injured more. All right, now let's look at kind of a practical application of this. Okay, we're going to look at some crash tests, and we're going to look at what does it look like if a car does a good job of protecting you? What does it look like if it doesn't do a good job? So this video shows some highly rated cars and some poorly rated cars. Okay, and just watch like the movement of the crash test dummy, okay, as they go through.